Hi there, this is Nuclear Physics Lesson 6 and this is half-life. So first of all I need to give you the equation for half-life. So essentially we should already know the n equals n naught E minus lambda t from last lesson. And half-life is, well, from GCSE, is the amount of time taken for half the given nuclei within a sample to decay. So it's the amount of time for half of the nuclei to disintegrate into something else. So we can say that the amount of nuclei remaining is half of the original amount. So n would be half of the original amount. That would be equal to n naught E minus lambda t. T is the half-life. So the n naughts cancel. So we end up with a half equals E minus lambda t. So we can take logs of each side. So it is log of a half. Now, log of a half, if you do mathematics, if you've done logarithms, you should know that log of a half is minus log 2. You can try that on your calculator, just to check. But log of a half is minus log 2. So I'm just going to get rid of that bit. So to get rid of E, we're going to take logs on both sides. So log of a half is minus log 2 equals minus lambda half-life in terms of time. Negatives cancel. So the half-life is equal to log 2 divided by the decay constant. So there it is. This is exceptionally useful if you've got the decay constant to get the half-life, or typically you might be given the half-life and expected to find the decay constant. So make sure that's written down. Remember to pause at any time if you need to, and let's move on. So we need to have a go at this question, and then I'll take you through it. So nobelium-259 has a half-life of 3,500 seconds. What is the decay constant of nobelium-259? So the equation, what we just got, is the half-life is equal to log 2 divided by the decay constant. So decay constant is log 2 divided by the half-life, and the half-life is 3,500 seconds. So that gives the decay constant that's equal to 0.2 times 10 to the minus 3 disintegrations per second. Very straightforward example. Let's do a bit more information. So substance X decays to substance Y with a half-life of 15 minutes. At 9 AM there are 1,280 nuclei of substance X. I want you to have a go and complete the table. Remember, every 15 minutes the amount of nuclei would halve. So the amount of nuclei X at 9 AM is 1,280. And the amount of nuclei Y is obviously 0. So at 9:15 we've gone 15 minutes, which is the half-life, so we half down to 640. And the 640 that have disintegrated will have converted into nuclei Y. So the 640 will half to 320. And then we need to add what's left onto the 640. So that will give us 960 in total. Same again, half to 160, add the 160 that's gone onto the 960 to give 1,120. Half to 80, add the 80 on to give 1,200. Half to 40, add the 40 on to the 1,200, so 1,240. So that should have been okay. Hopefully there's no issues there. Let's have a look at what's next. So if you want to write these down, if you haven't got it already, the half-life of a radioactive element is the time taken for half of the nuclei present in a sample to disintegrate or to decay. It is also the time taken for the activity of a sample to half its initial value. So here's a graph. And as you can see, after a time that is equal to the half-life, you end up with half of the original amount. And then after another half-life, you'll end up with half of this amount, or a quarter of the original amount. So if you want to write them down or make any notes, please do. And then I'll move on. Remember, you can rewind at any time. A few examples then, just to show the the varying degree of half-lives of different materials. So uranium-238, 4,500 million years, or 4.5 billion. Uranium-235, 704 million years. As you can see, they're starting to drop dramatically. Strontium-90, 29 years. Tritium, heavy hydrogen, 12 years. That's just a hydrogen with 2 neutrons. Technetium-99, that's used in hospitals. Radioisotope, half-life 6 hours, gamma emitter. Radon-224 down to 60 seconds. Helium-5, 1 times 10 to the minus 20, which is a 100th of a billionth of a second. So a wide degree of half-lives for different materials can, vary drastically by more than a factor of 30. Okay, so from this graph, I want you to just eyeball it and try and figure out the half-life from the graph. So remember, the half-life is the amount of time taken for half the given nuclei within a sample to decay. So you could just go from the 500 to the 250, go across, drop down, it's around 30 seconds. You could, if you really wanted to, be slightly more accurate, pick 2 values. So let's pick 400, it's about 10 seconds. And then half the 400 to the 200, which is 40 seconds. So the half-life is the difference between them, and obviously 40 minus 10 is 30 seconds. But that's the same as what we got originally. So, but that's up to you. Let's move on, let's do one more. Let's find the half-life for this material. So that should be pretty straightforward. So we start with the 800 and then just half it. So you get to the 400, we're around 20 seconds for the half-life. So half-life approximately 20 seconds. So they're pretty straightforward. Remember, you could do the one before where you pick the 600 and then the 300 and do the difference between the times. But I suppose it depends on how clear the graph is. This one's pretty clear, and the one beforehand was also pretty clear. Right, then a tricky question to end with, to finish the lesson with. So the example is calculate the activity of 3 micrograms of copper-64 if it has a half-life of 13 hours. So let's pause and have a go at this one. It's quite a lengthy one. And then I'll take you through the answer. So we want the activity. So the activity is lambda n. I've done quite a few of these before in previous lessons. However, in this scenario, we need to find the decay constant and the number of nuclei. So let's find the decay constant first. I'm going to find the decay constant, then clear the screen, just to ensure that we've got enough room. So the decay constant would be log 2 divided by the half-life. And the half-life is 13 hours. And we need to turn that 13 hours into seconds. So it'd be 13 times, we got 60 seconds and 60 minutes in an hour, which is 3,600. So it will be log 2 divided by 46,800, which gives a decay constant of 14.8 times 10 to the minus 6 disintegrations on average per second. So that's the decay constant done. Make sure that you've got this written down somewhere. Now let's find the number of nuclei. So we need to find the mass of an individual copper-64 atom. So that would be the molar mass, so 64 grams per mole. So that would be 64 times 10 to the minus 3 kilos divided by Avogadro's number, 6.02 times 10 to the 23. So it's the mass of an individual atom of 1.0631 times 10 to the minus 25 kilos. then we need to be really careful. We've got 3 micrograms, so it's 3 micro, which is times 10 to the minus 6, but then we've got the grams as well, which is times 10 to the minus 3. So the total mass of copper is 3 times 10 to the minus 9 kilograms, divided by the mass of each individual atom, times 10 to the minus 25, gives us the amount of atoms as 2.8219 times 10 to the 16 atoms. So activity is lambda n. So we just need to multiply that by the decay constant from the last question. Well, not last question, the first part of this question. I'm just going to write it in. So multiplied the number that you've got written down, which should be the 14.81, times 10 to the minus 6. And those two multiplied together will give the activity, because activity is lambda n, of 4.2 times 10 to the 11 becquerel. Hopefully that one went okay. Thanks for watching that video. I hope it helped, and I'll speak to you soon. Thank you.